Okay, nice to see everybody. Welcome back. I'm glad to see you survived the midterm. We didn't scare the entire class away. That's great. Um, let's see, moving forward, your next homework, or your homework is due Wednesday. Oh, okay, good. So you've got a homework due Wednesday. Don't forget about that. Many people in my office hours got started, which is great. And then another homework will go after that. Very simple course. So basically, the remainder of the course, you have your homeworks, your quizzes, and your final exam, and you're out of here. So congratulations, you're halfway through. All right, any logistical concerns? To the person who's about to ask me when you'll get your midterm score, my answer is when we get around to grading it. But we'll try to get it back to you before the drop deadline, because I know that's the thing. Okay. Excellent. So today, your instructor is very tired, but we're going to try and make it through a particularly hairy set of calculations together. This had an unfortunate alignment with my having to drive back here from the Cape at 6 a.m. this morning. But we're going to make it through together, and if I fall asleep, just like throw something, and I'll wake back up. So for those of you who are picking up our story again after a little while of a break, remember that essentially what we've been studying the last couple lectures is optimization, right? So we're given access to some function f, which takes a point in Rn, and maps it to a scalar, and our job in life is to try and find local or global minimizer. Typically only local unless we can say something about f, for example, convexity or quasi-convexity, right? So hopefully that story is familiar. And in our previous lecture, we began to suggest some basic strategies that people use. Now, the idea here is if we kind of look generically, we can think of a lot of techniques as sort of following the following outline, which looks something like this. So here, remember that xk is our current iterate of optimization, right? And we're trying to find an xk that minimizes f as much as possible. And we proved a little lemma in our lecture last time, which says, at least for very small multiples of the gradient of f, if I step from xk along the gradient direction just a little tiny bit, then the value of f decreases. Yeah? And again, that's one of these little lemmas that I think we all kind of know and love, right? In some sense, the basis of the gradient descent algorithm that many of you use every day. But actually, as we might remember, it isn't actually entirely obvious. You have to justify the fact that moving along the gradient actually decreases your function. But in any event, we did, using Cauchy-Schwarz inequality. And that suggests the algorithm on the board, where a couple lectures ago, we talked about one-dimensional optimization algorithms, like Newton's method, golden section search, whatever. And what we could do is define the restriction of f to the line through x in the gradient direction, right? That's this function g. Hopefully that sentence parsed. That was a lot of math words in one. Cool. And then we can say, oh, well, now we have a one-dimensional optimization problem for finding t, like our step size, our learning rate, whatever you want to call it. And then we can essentially take the gradient, scale it by t, add it to x, and that's our next iterate. Yep. Now, this particular technique is called gradient descent with line search. The procedure for finding a t is called line search. And as you might remember, there's this little push-pull, right? On the one hand, we could work really, really hard to find the actual minimizer of this function with respect to t, but in some sense that feels wasteful, right? Because if you're optimizing really, really hard in t and to the 50th decimal point, then at some point you're gonna, decide you're happy with that iterate, take a step, you recompute your gradient, and you keep going, right? So there's sort of an inner loop and an outer loop that you have to balance in these techniques. The outer loop being the individual recomputations of the gradient, and the inner loop being choosing a step size so that the function decreases, right? And so this is a very typical theme of advanced numerical algorithms, that you have a numerical algorithm with another numerical algorithm inside of it, right? In this case, you have multi-dimensional optimization with one-dimensional optimization hiding inside of it. And there's sort of two different ways that you can go about that. One of them is to just optimize the heck out of the 1D problem, which probably will lead to convergence, but could be awfully slow. A different one is to sort of go back to your proof of convergence of the outer problem and ask what conditions you really need for that outer thing to converge. In particular, did you really have to solve this one-dimensional optimization problem to full optimality? And as we suggested in our previous lecture, the answer was no. So in particular, one thing that you can check is that this set of conditions called the Wolf conditions are sufficient for line search. I'll refer you to the previous lecture for sort of some pictures of why these conditions make some sense, rather than going through them a second time. But essentially the basic idea here is that so long as you can manage to find a tk that satisfies these two inequalities at every step of your gradient descent with line search procedure, you will reach a local optimum of the optimization algorithm. One thing that's not entirely obvious, which I guess is an exercise left to the reader, or maybe an exam question, that would be fun. So if dk is the descent direction, like minus the gradient, right? One thing you should double check is that there exists a t that satisfies these inequalities, right? Otherwise, these would not be very useful inequalities. And one thing you can check is that's actually always the case, so long as you have a descent direction, okay? So this is one very generic strategy for optimization, where you just keep recomputing dk. Often it's minus the gradient, but we'll see some examples later where it's not. So for example, minus the Hessian times the gradient might be a good search direction, because that's sort of suggestive of Newton's method, right? But this algorithm still has the kind of annoyance that we have to recompute tk in every step. In other words, we have this sort of outer loop and inner loop. The outer loop is trying to do optimization. The inner loop is trying now to do line search, which we decided is ever so slightly different. And those two things are competing against each other to reach a local min. Now, for many of you guys, especially in 2025, I feel like I encounter a lot of students whose background is in the machine learning world. This algorithm feels a little bit unfamiliar because we're not used to having this line search procedure. And a large reason for that is that even the gradient you compute in that universe is pretty unreliable, right? So specifically in machine learning, typically you get a stochastic estimate of the gradient, and then it's not so clear that these line search procedures can really succeed. Like every time you query your function f, you get a different function value just by virtue of using random number generator, which feels like a problem. And so in that community, and in many other ones, the standard is not to use line search, which, by the way, does lead to faster convergence if you can do it, but rather to use a simpler procedure, which is to just use a constant for this step size tk, right? By the way, in that world, I guess instead of step size, that didn't sound techno enough, so they renamed it learning rate. So I'm sorry, my college friends are like blowing up my phone, and I need to just turn off notifications. Jesus Christ, people. All right, mute. Right. So that leads us to the topic of our discussion for today. Hopefully we'll get a little farther than that. We are slowly slipping behind our course schedule, but that's okay. Which is, rather than doing a fancy adaptive search for this constant tk in every step, or not constant rather, we want to come up with some policy for just using a constant learning rate, or a constant step size, or maybe not even constant, but just some function of k that's predetermined rather than having to recompute it every time. Okay? And so there are a lot of different ones out there. Today we're going to talk about the simplest case, which is when is it sufficient to just use a constant for tk. But it turns out if you go out there in the machine learning world, you'll see that people use all kinds of wild and crazy strategies for choosing tk. I think the two desiderata that I've listed on the screen are two very typical ones that avoid some of the situations that we discussed in our previous lecture. So on the one hand, you might want your tks to approach 0 so that you're not like hopscotching over your local minimum. So a good example to think about if you want a nice counterexample for a lot of optimization techniques is a function that just looks like absolute value, right? Because here, what is, I guess this is absolute value of x minus x naught, because for some reason I decided not to draw it at the origin. What is the gradient, or in this case, the derivative on the left of this dotted line? Yeah, so it's just -1, right? So this is dy dx equals -1. Over here, I'll save you all the pain, since apparently that's slow this morning. It's +1. Oops. So will gradient descent with a constant step size ever converge for this function? When I say converge, I mean like actually reach the minimizer? No, right? So like if I have a step size, eventually, you know, I'll ping pong over here, ping pong back, and so on in the best of possible circumstances, right? Or if I'm really unlucky and I like ping pong too far, I might spiral out of control, right? So these are the kinds of functions we have to worry about. By the way, I've drawn absolute value, but if you're worried about differentiability, I could have added like a little slurp on the bottom of that function. It wouldn't have changed anything. Yeah, it's a technical term. So in any event, because of counterexamples like this, people say, well, okay, I need my step size to go to 0 so that eventually my algorithm converges. To give a really stupid, let's say that I remove this second condition. One thing that I might do is choose like t k equals 2 to the minus k, right? That goes to 0. And actually, gradient descent is a good example where this is a really ineffective optimization algorithm. Do you guys see why? So let's say that I start somewhere far, far over here to the left. This is x naught for my optimization technique, right? And I use a step size that looks like 2 to the minus k. That's kind of nice. It goes to 0. And I am moving along the gradient direction in every step, right? But what's going to happen? Well, I'll take a step of size 2, and a step of size 1, and a step of size 1/2. And my iterates will converge, but I didn't actually reach a local minimum because the coefficient in front of my gradient was vanished too quickly. You see that? And so actually, this is one of these kind of funny corners of math where you want things to go to 0, but you don't want to go to 0 too fast. So typically, these two conditions are needed in this universe where you have a sequence of step sizes that approaches 0, but also sums to infinity. Can anybody give me an example of such a sequence? Yeah. Yeah, 1 over k, I think is a very typical one. Now, does this matter in reality? No. People do all kinds of wild things in training optimization models in machine learning, but if you really did care about convergence, you'd need some conditions like these guys. And indeed, today we're going to talk about a very simple proof of convergence for gradient descent procedure that doesn't rely on these. A slightly extended version of that proof will show that for a broader class of functions, if you add these two conditions, convergence will still happen, which is even nicer. Okay? But does everybody kind of understand the name of the game here? So we're moving away from line search toward just kind of policies. Sometimes people call these learning rate schedules for choosing TKs. And these are the kinds of conditions that you often see. Now, in reality, if you are an engineer in optimization, people do all kinds of wild and crazy stuff. So for example, one popular one in machine learning for a while was a cosine schedule, which I find just totally wild, where the learning rate does something like that. I don't think there's much theory out there that justifies that, but I think this sort of mythology was kind of like some explore, exploit kind of thing. Like for a while, you're moving wild and crazy, and then you like converge a little, and then maybe you jump out or something. I don't know. There's like a lot of, when the explanations of these optimization algorithms start getting kind of spiritual, I drop off. But in any event, there's a whole, like if you open up PyTorch, you'll see there's a whole like library of these things you can play with. My suggestion would be to not do that, and if you are doing that, you're probably in the regime where you should have fixed some other part of your model. But what do I know? Okay, so today we're going to present you all with this extremely elegant theorem here. It's a little bit messy to state, but actually is quite straightforward. So the basic idea here is that I want to do gradient descent, and in particular, I want to do gradient descent with like the world's least interesting step size. So in particular, I'm going to just use an algorithm that takes the following form, which is just xk is equal to xk minus 1 minus t gradient f xk minus 1. And now t is just going to be a constant in this case. Okay? And the question we're going to ask today is, like, does this thing have any hope of converging? And when I say converging, I don't mean getting close to a local optimum. I mean actually reaching it. Yeah? And what we're going to find is that actually, kind of surprisingly, I think from these kinds of counterexamples, which make you feel like maybe you can get close and then you're going to ping pong around the minimizer, it turns out that this notice that like I had to add a little, like this function has a little point in the bottom in order to construct this counterexample. What we're going to see is that in fact that's sort of a necessary condition. In other words, if I choose a t which is small enough and my function is positively curved enough, those two things together are going to be sufficient for gradient descent to converge, which is kind of cool. Okay? Right, and so essentially this is a useful property. We're going to prove it for convex functions that are twice differentiable, so this is the nice case. I think in reality what you'll see is that this proof is kind of local, right? It depends on these conditions holding at each step of your algorithm. So the reality is that once like, typically you have some crazy optimization landscape, it's all over the place, and then eventually you get somewhere close enough to your minimizer that these theorems begin to kick in. I think this is the schematic that we often draw. So we're not going to talk about what happens in far away from these points, but it will at least kind of justify that like as soon as we're in this regime where things are bowl-shaped with a little bit of curvature, then even the goofy version of gradient descent converges. Does that make sense? Okay. Now, in order to do that, we do need to put some assumptions on our function f, right? In particular, we need to avoid this pointy case. And so one way that we can do that in mathematical formalism is to add a condition called Lipschitzness. I struggle with that word, which is essentially the following condition, what it says is that the gradient of f evaluated at x, and by the way, this is for Lipschitz gradients, right? So Lipschitz, and this for a function is a bound on its slope. I'm concerned about a bound on the rate of change of the gradients themselves. So this is kind of like a second derivative bound. So it looks something like this. When I say something, I mean I'm reading it off of my screen. OK. So here's the idea, is that there exists some positive constant L. And L needs to be uniform. If it depends on x and y, then this is not a Lipschitz function. In fact, it's not a nothing function, because then it doesn't say anything. So there exists some positive L so that the difference in gradients is upper bounded by the distance of the points. Now this expression might seem kind of arbitrary, but if you divide both sides by x minus y, notice that this is kind of like dy dx. And in fact, you can think of this as kind of like a bound on the Hessian of f, right? But like a little bit non-local. Does that make sense? Any questions so far? OK. So what we're going to show, by the way, do we want L, like, do you think optimization is going to be easier when L is big or small? Small, right? Because that's sort of a tighter bound, right? So as L gets small, our function kind of begins to reach the one where the slopes are barely changing at all in every step. And that turns out to be the kind of nice case for this particular technique. Okay. So what are we going to show? We're going to say, suppose f is convex. Remember what that means, that it lies below its graph. We'll come back to that in a minute. And twice differentiable with a Lipschitz constant L. So here, the Lipschitz constant is on the derivatives. Moreover, suppose the minimum is attained at some x star. By the way, kind of a funny thing about this proof is that if there are more than one x star, it kind of doesn't matter which one you choose, which is odd, but it has to do with convexity. Then essentially, gradient descent on f with constant step size t, as long as it is upper bounded by 1 over L, is going to satisfy this particular condition. OK? And if we kind of glance at this, let's see why this is telling us what we want. Notice that essentially, on the right-hand side, x0 minus x star is a constant, right? This is the distance from where we started to where we want to go. And it is being divided by k, right? So as we get farther and farther along, this right-hand side is going to 0. And on the left-hand side, it's saying that if I evaluate f at xk and f of at x star, those two things get closer and closer to one another. Sanity check, why do we not need an absolute value around these things? Yeah, x star is the minimum. So that difference has got to be positive, yeah? Or at least not negative. OK? Now, notice I think this theorem is actually very typical of the optimization world in that it's kind of quietly hiding some issues that we talked about in the first lecture or two of this course. Namely, what are we measuring on the left-hand side of that inequality? Do you remember? Yeah, but specifically, we're measuring the distance between our current value of our function and the value at the optimal point. Does that actually tell you anything about the distance between xk and x star? Me, you started to say something. Nice haircut. That's exactly right. This is backward error. It could actually be the case that xk is really far away from x star. It's just that our function got really, really, really flat. And this kind of theory is unable to distinguish between the two. Now, if you return back to that Lipschitz condition, in this particular case, you can kind of put those two things together and come out with some distance bound, but it won't be very good. Yeah? Now, on the other hand, for optimization procedures, this is probably good enough for most of the things we care about, right? What it's saying is that, like, we found an xk that achieves the optimization objective value which is pretty close to the one we can get in the best possible world. Yes?
How does the Lipschitz come in? Because like the Lipschitz is
The Lipschitz is on the gradients. I believe if you are in a compact set and have a bunch of other conditions, you can then get a Lipschitz constant on the function itself. But I'd have to think it through a little bit. Yeah, good question. OK, so does everybody understand the theorem that we're going to try and prove? Like some acknowledgement would be useful, like open eyes, awake, look up from our laptops for a second. Sweet. OK, here's the thing. I'm going to get it totally wrong because it's very technical and yucky, and I'm very tired and kind of need to go to the bathroom. So that's what we're going to do together today, OK? So I've separated my proof into a short lemma to begin with, and then we're going to prove the main result. And this thing is basically just a giant pile of Cauchy-Schwarzes and triangle inequalities. Everybody's favorite things. Yeah. That's, you know, like in Jersey Shore, Snooki is always saying, like, it's my best thing, which I always thought was a useful phrase. People are killing me. Okay. So, right. So we're going to begin with like a little bit of a lemma, which is basically a convenient inequality that we're going to use in our proof. Incidentally, this proof is sort of a simplified one from one that I found in a fancy stats textbook, but it's my own proof, meaning that not only am I likely to get my own proof wrong, the proof itself might also be wrong. So I need you to all pay attention together today. Okay? So in particular, we're going to start with a useful little formula here, which is suppose we take any xy in Rn, then we're going to show the following bound, which is that f of y is less than or equal to f of x plus grad f of x dot product y minus x. Now, so far, this looks like the linearization of f, right? But we're going to add a term, 1/2 L times y minus x squared. By the way, is this enough to answer Hamid's question earlier? It might be. I'd have to think about it. Okay. In any event, why might we want to do that? Let's draw a little bit of a picture of what this lemma is trying to tell us. It's always important when you read theorems to kind of, like understand the spirit behind the thing. Okay, so we have a convex function f, so that's like roughly bowl shapes like that. And let's see here. So let's say that I choose a point here. Notice that the first two terms are the linearization of f. Now, one thing that you might be able to kind of guess about convex functions is that they sit above the linearization, despite my bad drawing skill. So like f has to sit above the line that I drew. Ignore this little intersection here. That's my bad. Okay? So that's going to be, what we're going to try and do is to sandwich our function a little bit. So we've managed to kind of sandwich it from below, bound it from below. I suppose we haven't sandwiched yet. It's more of an open face situation. Okay, but on the other hand, it turns out we can also bound it by above. And the way that we're going to do that using this lemma is to like stick a little parabola sitting on top of it, which is going to come from the Lipschitz constant here. Right? And that's going to be useful for us because essentially when we do gradient descent, what we're going to know is as we move along our gradient, we kind of sit in between these two things. And this is actually true for any y. That's a nice byproduct of convexity. Does that make sense? So this is our sort of convenience lemma. It's like a little sandwich. We like sandwiches. Okay. Do you mind if I erase this little picture so that I have some space to write like lots of ugly equations? Okay. Brace yourselves. So, actually, this really isn't so bad. I'm talking it up, but actually, this is pretty simple. Okay. So we're going to define a very simple function, phi of t, which we're just going to call f of x plus t y minus x. Right, so basically I'm just drawing a straight line from x in the y direction, and I'm looking at the slice of my function f between those two things. Okay? Now, we're going to use a theorem that I hope you all know and love, which is the fundamental theorem of calculus, FTOC, which says the following. The value, phi of 1, is equal to the value of phi of 0 plus the integral from 0 to 1 of phi prime of s ds. Everybody agree with me so far? Good. We're starting out easy today. All right. Well, essentially, our little lemma here is going to follow directly from the fundamental theorem of calculus. We're just going to plug in this particular choice of phi. Okay? So what is phi of 1? Somebody help me out. Yeah. F of y. What's phi of 0? Somebody else. I'll wait. Thank you. What of x? F, that's right. Okay, plus the integral from 0 to 1. And now phi prime is a little bit annoying, but we're going to apply the chain rule here. And what are we going to get? We'll get, okay, we got the gradient of f evaluated at that point. So x plus s, y minus x, like that. Dot product, and then the derivative inside with respect to t is just y minus x. ds. Everybody with me so far? This is just chain rule. Cool. I heard a lot of complaints about your midterm that I dared to expect you to remember the quotient rule, and I feel no guilt about that. Also, you can derive it. It's like a one-liner. Okay. So, yes, Alicia. Yes, ma'am. S. That's right, because the integral is with respect to s. That's right. So there's this yeah, I sneakily swapped our notation a tiny bit. Yeah. No, this is the gradient of f with respect to its input, which is like a point in Rn. Right, so this is the chain rule, right? It's the grad of f times d over dt of the thing in the inside. Yeah, good questions. Anybody else? Keep me honest. You keep me young. Okay, so we wanted a theorem of this form here, but we don't have it yet. So one thing we can do is just say, okay, which by the way is just like a good thing in life. Like I want to prove something, and I don't know how. I'm just gonna like start smushing things in that I want to be there and just see what happens. Yeah. So in particular, well, what is this thing? Well, it's equal to f of x, like before, and maybe I just stick in this linearization term and then I subtract it again, just for fun. Okay, we're friends here. So we have grad f of x dot product y minus x. Now we're going to cache in the back of our head like, oh crap, I need to subtract this thing because I really just want to add 0. But we're going to forget that for a second and add this third term here. Okay, so what are we going to get? Well, we'll have the integral like that, plus, sorry. I'm going to add brackets here. We have this grad f, x plus s y minus x. I warned you guys that it's going to be a little bit technical today. We're doing the technical challenge, to use the terminology of the British baking show. But we have a grad f there. What I'm going to do is just subtract it off there. We're going to group things together kind of nicely. So this is minus grad f x dot product y minus x ds. Now, why is it okay that I did that? Let's think for a second. Notice I have grad f dot y minus x. Then I've got a minus grad f dot y minus x, but it's integrated with respect to s. But that's sort of okay because s is just integrated from 0 to 1, and that thing has no s dependence, right? So this is just the world's most complicated way of multiplying by 1. Yeah? Actually, we have a few contenders for that in this class, but that's 1. Yeah? It is 1. Huh. Okay. Questions so far? Okay. Now, we'd like an inequality to happen, but we haven't done any inequalities so far. So maybe this is a good juncture. And remember what we're aiming for. We now have the first two terms we're pretty happy with. So in some sense, we just need to bound the third guy, right? And what did we want? We want it to look like the Lipschitz times y minus x squared. So far, we have this ugly thing. But notice there is a y minus x hanging there. That there's a hope. What can we do? Any ideas? You're always answering questions, aren't we? Yes? We're going to need to use the Lipschitz, but Lipschitz is on grad f. Grad f is currently not inside of a norm, which is what I need for Lipschitzness. Lipschitz-ism? We'll come back to that. Yeah? The Cauchy-Schwarz inequality. You guys remember this one? So we've got a dot product between two vectors, which is upper bounded by the product of their norms. Okay? So let's write that expression. So we have less than or equal to f of x plus grad f of x dot product y minus x plus the integral from 0 to 1 of the product of the norms of these guys. All right, fine. I'll write it. It's fine. X plus s y minus x, like that, minus f of x, not squared, sorry, but it is the 2 norm, times y minus x ds. Cool? Now, whoever it was, your intuition was absolutely right. Like, we want to use Cauchy-Schwarz was one person's intuition. The other one was we want to use the Lipschitz constant. And now, notice we can do that, right? Because this first term is upper bounded by the difference between the things going into f times the Lipschitz constant. Yeah? By the way, does this norm have any s dependence anymore? No. So I can just move it out of the integral. Cool? All right. what is the difference between the arguments of these things? We have x plus s, y minus x. And then we've got x. So if we subtract these two things, this is going to be s, y minus, or just, yeah, just s, y minus x, right? That's the difference between their arguments. I said a lot of words, and for that I apologize. X plus s, y minus x, this quantity here, minus this quantity here, is just that piece there. So when we apply the Lipschitz thing, I see like 6 hands. Oh no, what have I done wrong? Oh yeah, that should be grad, sorry. Thank you. I can never tell when you guys are paying attention, but when I make a mistake, then you wake up. So like this is, you're teaching me a bad lesson. Likely it's like not a lesson I need to learn because I'm making mistakes all the time anyway. Okay, so in particular, this is less than or equal to the Lipschitz constant times s times the norm of y minus x. That makes sense? So in particular, this norm here is less than or equal to L times s y minus x. That make sense? Cool. We're almost done, I promise, with the lemma. And then we do more inequalities. Today's a big day for me. I'm having fun. OK, I had a lot of coffee. So, right, so let's rewrite this thing. This is f of x plus grad f of x dot product y minus x. And now we've got, notice we've got 2 y minus x's there, so that's kind of fun. Right? We've got a Lipschitz constant. And now we have the integral from 0 to 1 of s ds. Everybody with me? All right. Calculus exercise. I know, I'm sorry. You're gonna have flashbacks to the AP exam. It was a tough time. High school was coming to an end. We were playing that vitamin C song. It was close to graduation. We had to do the integral of s ds from 0 to 1. These are very 90s American references, by the way, so I'm realizing with my classroom full of mostly non-American graduate students, this is probably lost, but I am entertaining myself, and that's fine. So what is this integral? 1/2, that's right. Because remember, this is 1/2 s squared from 0 to 1. So in particular, this is f of x plus grad f of x transpose y minus x plus 1/2 L y minus x squared. And I haven't checked in a while with the statement of our lemma, but hopefully that is indeed what we wanted to prove. Ta-da. OK. So we now have one big ugly formula, and we're going to use it to prove another big ugly formula. Cool? Yes, Jonah. No. No, it shouldn't. Yeah, that's a 1/2. Yeah. Any other questions? Yes.
Can you remind me how this formula relates to the picture you drew of the linearization?
Sure.
Relative to the function?
Right. So essentially, notice that the right-hand side of this is the linearization of f plus a quadratic term, right?
Yeah.
Now, if you didn't have that quadratic term, the inequality would actually go the other way around by convexity, right? So basically, we've got the picture to have in mind. Like here's x, right? Yeah. And then y. So it's like sitting above this line by convexity. Now, if you add the second term, right? This is a parabola in y minus x, so it's kind of like that. By the way, it doesn't have to be tangent or anything else. I guess it does have to be tangent, but does it? No, actually. It's just some parabola sitting there, right? What we've shown is that it sits underneath this guy. So we've sandwiched our convex function between two other convex functions, which are kind of like nicely behaved. Right? So essentially what we're going to prove, like our gradient descent algorithm in some sense, is going to show that like it's somehow no worse than gradient descent on the thing sitting on top, and it doesn't like zip too fast like the thing on the bottom. That's what we're going to do. Oh no, I lost my notes. OK. Any other questions? This is great. OK, so now we got to prove our actual proposition. By the way, I'm going to pause for a second. This classroom is tricky. I don't really want to use this board here. Have we bonded with this proof enough that if I leave the statement of the lemma, I can erase the proof? I know that's annoying to students. Yeah? You're not just being agreeable with me? Okay. All right. I'm sorry. And now, like, this is roughly the moment when somebody says, stop, 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 stop. Okay. All right, team. We successfully did it. We kept our lemma here. So here's what we're going to do. We're going to make a very specific choice of y, and that's going to basically choose our lemma off right, using a really sneaky trick involving telescoping sums. So we're going to choose y to be x minus t grad f of x. So think about what's going on here. So y is like the result of doing one step of gradient descent starting at x. Okay? And t, we actually know a tiny bit about t from the statement of the theorem, which is t is less than or equal to 1 over L. We're going to munge all these things together into one big, beautiful proof. Okay. So from our lemma, we have f of y is less than or equal to f of x plus grad f of x dot product y minus x. But what is y minus x in this particular case? It is minus t grad f of x. Yeah. Okay. Plus 1/2 L y minus x again, which is in this case L t squared grad f x squared. Everybody see this is just an application of our lemma? Cool. All right, so let's write this in slightly less weird notation. In particular, I'm going to do a hot swap, or whatever they call it. I'm just going to pull the minus out rather than rewriting this whole thing. Okay, so this is really minus t times the dot product between grad f and itself. Yeah. Which is really minus t. I'm so sorry. I promise I won't do this again. I'm regretting it already. This is minus t grad f squared. Okay? This is just a cleaner way to write the same thing. Okay. So, what are we to do? Any ideas? Well, we kind of do, we know one thing, which is we actually know a bound for L in terms of t, or vice versa, right? Remember that we chose t to be less than or equal to 1 over L, right? So, in particular, which way do we want to go? Let's do this in terms of t, okay? So, what does this say? Well, it also says, by the way, that 1 over L is less than or equal to t, right? These are all positive numbers, so we can do these kinds of things. Okay, so in particular, if I do that, I can substitute in a t for that. Oh, sorry. Oops, wait, I'm confusing myself. No, sorry. I'm very tired. L is less than or equal to 1 over t. My apologies. It's harder up here than you would think. Okay, so in particular, I can get rid of this L and substitute in a 1 over t. Conveniently, that is going to cancel one of the t's and the t squared. Cool. So this is really plus 1/2 t grad f. Yeah? At least upper bounded. We have minus t grad f. So overall, what we justified, that this is less than or equal to f of x minus 1/2 t grad f x squared. Now this is looking pretty nice, huh? Like now we're getting somewhere. Okay. Now, we're almost done with our yucky analytical argument, and then we're going to switch to a yucky combinatorial argument. Cool? Okay, so now we're going to apply convexity. So far we've done kind of a nice thing, which is that, like, at the very least, notice, by the way, what is this bound telling us in life? It's actually kind of a useful bound. It says if I take one step of gradient descent, right? Remember that's what y is. I have actually shown that I have to make at least this much progress, which is kind of nice. Okay. So now, somewhere in our theorem, we need to start inserting an x star. So that's our next goal. Yeah? And so to do that, we're going to apply convexity to upper bound f of x star. Remember that we showed that convex functions sit above their linearization. So in particular, we can say that f of x star is greater than or equal to f of x plus grad f of x dot product x star minus x. Does that make sense? I think it's kind of weird because we're used to thinking of convex functions like the f of x star is like sitting underneath stuff. But in this particular case, I linearized at x, right? So that straight line has to sit under the actual function. And in particular, it has to sit underneath x star. Cool? All right. I think we're done with like random fun like trivia facts about analytical functions here. Now we just have to glue them all together. OK, so we have two ingredients. We have ingredient 1, and we have ingredient 2. And we're going to put them together to make an even nicer bound. OK, so in particular, here's what we're going to bound. In some sense, remember our goal. We're trying to bound like the progress that we made in gradient descent. So it might make sense to bound the following quantity, which is f of y minus f of x star. Right? Because if we can somehow bound that in terms of f of x minus f of x star, then we kind of know how much the left-hand side of the inequality is changing in each step of our algorithm. Cool? All right. So we put these two things together. Notice, I wish I were like a foot taller. We have a bound on f of y. Sorry, I should use half. We have a bound on f of x star, and conveniently the inequality goes the other way. So when I put a minus, then the stars align. OK, so in particular, what is this thing going to be less than or equal to? Well, notice the f of x terms cancel. So we're left with grad f of x dot product with x minus x star. And then we still have this additional curvature term, 1/2 t, grad f x squared. Sorry, I'm like running out of steam. I'm tired. OK. Everybody with me so far? See how 1 and 2 lead to 3? OK. Now here's the thing that we can do, which is kind of ugly. Again, no. We can be kind of optimistic and start to factor out an expression that looks like the right-hand side of our inequality. So in particular, I can factor out a 1 over 2t, like that. And now multiply through by 2t here. So we have 2t times grad f of x dot product x minus x star, like that. Minus, we have a 1/2 went away. But unfortunately, we now have a t squared times the grad f squared. OK. I haven't done anything too profound in that particular line of math. OK. So now, here's kind of a fun thing that we can do. We can add and subtract the following, which is x minus x star squared. We subtracted it, so we have to add it back. Like that. All right. Now, why might I want to do that? Well, essentially, in some sense, in our inequality, like this is not so great. What we'd really like to do is to insert a y in there, which is like x minus this thing, scaled by t. And so that's what this additional term is going to allow us to do. In particular, I think I'm going to leave it as an exercise for you guys, because this is literally just expand the square, combine terms, and put them back. OK? But we've done that about 50 times in this class. We will get the following expression. Oh, yeah. 1 over 2t. And we're going to, sorry. These should be scaled by 1 over 2t. Obviously, I can do that. Still be 0. OK, so when I do that, I will get x minus x star squared. So basically, that is this term here. We're just going to leave it alone. And it turns out you can combine all of the other terms into the following: x minus t grad f x minus x star squared. So again, so you get from this line to this line, you just take this giant square and you expand it the heck out. Let's see if we can eyeball it really quick. So notice that we have an x minus x star squared is going to come up. You've got a t grad f with a square in front of it, so those guys kind of match up. So notice that we're pretty sure it's going to be okay. Is everybody okay with me skipping writing out every single term in this product? Please say yes, because I'm tired and I have a chalk allergy. Okay. All right. But again, just to repeat a fifth time, to get from here to here is just expanding this square. That's it. Okay. Well, what is this thing? Notice that this guy is just y, right, by definition. Right. So in particular, this expression is actually pretty nice, I promise. It is 1 over 2t x minus x star squared plus the norm y minus x star. Oh, that's a minus, sorry. Squared. Okay. That's just by definition of y. Now, one thing that's important to do when you write these giant chains of inequalities is to go back and remember what it was you were trying to show. So in particular, all the way at the beginning, we have f of y minus x star. And now we've got kind of an intriguing expression here. Do you see that? That we've got x minus x star and y minus x star. And remember that x and y are subsequent iterates of our algorithm, right? This is kind of handy. So think about what, just for fun, and because it's obviously the next step we're going to do in this proof. What would happen if, so I'm thinking of y as xk plus 1, something like that. What if I now summed this over all k's? Do you see what's going to end up happening? This is beautiful. In one term, you're going to have a minus, but that's the next term, where the previous term had exactly the same value as a plus, right? This is just the next term in the sequence, but with a minus in front of it. Okay? So in particular, let's write this out more carefully. Dare I use my little nub of a board here? Yeah, sure. Here's what we're going to do. So we're going to think of xi as the ith iterate of gradient descent. And in some sense, if we want to get a really lame bound on the error, rather than just bounding a single error, we could bound all the errors summed together, right? That's kind of worse, yeah? So in particular, I can write, what is the sum from I equals 1 to k of f of xi minus f of x star? Well, okay, so we can apply the previous inequality here, where each time y is going to equal basically I plus 1, xi plus 1, and then x is going to be xi. Does that make sense? Because remember that y is after one step of gradient descent. This is a technical proof. I'm sorry, it's just ugly. Okay, so in particular, what is this thing? Well, if we apply this inequality here, we've got a 1 over 2t and a sum. I'm going to shift my sum to 0 to k minus 1. We'll see why in a second. Of xi minus x star squared minus xi plus 1 minus x star squared. Okay, let's see if we all believe this thing that I wrote down. So I took a bunch of steps of gradient descent, and each step I compared it to x star. If we go back to our inequality here, I'm running out of steam. I just got to make it to 12:30. I'm going to go to sleep. Okay, so we showed that in the next step of gradient descent, we can bound it in terms of the previous step. So that's why I shifted our sum to be from 0 to k minus 1 instead of 1 to k, right? Because now we're doing next step, current step, right? Notice next step, current step. So I just applied the inequality we derived k times. Cool? All right. Now here's something really cool. Take a look at what happens. So this is x0 minus x star, x1 minus x star. And then we got x1 minus x star, x2 minus x star, x2 minus x3, and so on. This is called a telescoping sum. You guys know this trick? So in particular, this object is equal to 1 over 2t times basically just the two terms that persist, which are kind of like our fence posts at the very ends of the sum. So in particular, this is going to be equal to x0 minus x star minus xk minus x star. Like that. Ta-da! Cool. By the way, so norms are positive, so this thing is less than or equal to 0. So just out of laziness, this is less than or equal to 1 over 2t x0 minus x star. Like, finally, we're getting somewhere. Do you guys see that? Like, we're comparing values of f at the iterates of our gradient descent. And now, what have we shown? We've shown that they're upper bounded by something that has no k dependence. However, we're not quite done. Do you see that? Because this right-hand side is some positive number. And what we want is convergence, like actually goes to 0. And we don't got it, because t is just some positive constant. Does that make sense? But notice, if we're comparing the inequality we want to the inequality we got, if we look on the left-hand side, there's also something different, which is the sum over a bunch of terms rather than just one term in the sum. Yeah? OK. Now, what we're going to do, this proof is so sneaky. Remember that we showed at the very least that the error that we made, like we never kind of go backward in gradient descent. It's like purely monotonic in our particular universe. OK. So in particular, notice that the difference between f, say, 7 and x star, right, that is strictly larger than the difference between x10 and x star. Right? We showed that at the very beginning of our argument, that essentially f never goes up, right? So what does that show us? So remember, our goal in life, let's see, can I squeeze in this little bit of board? I think I can. We'd like to prove a bound on fxk minus f x star, like that, right? We're going to do a really, really weird thing. I love this little proof, which is this error is strictly larger than the error in all the previous terms, right? So in particular, this thing, or is strictly smaller rather, is less than or equal to the average equals 1 to k of xi minus f of x star. Do you guys see that? Essentially what I'm saying is that the average error of all the past iterates is larger than the error of the current one because I'm always going down. Why is that useful? We're like 2 seconds from being done with this proof. If we look at this previous inequality, notice that that's exactly what we bounded without that factor of k. So in particular, from the previous inequality, we have 1 over 2kt x0 minus x star squared. Ta-da! And that's the thing we were trying to prove. So let's go over our proof again, because it like combined like 16 different little things that we needed. So in particular, let's think for a second. We began by proving a little inequality, which I've since erased, which is basically trying to sandwich the values of f for Lipschitz things that are also convex. And notice that around optima, this is actually typically true for differentiable functions, at least some neighborhood. OK, so now what did we do? We basically used that inequality to sandwich the behavior of what happens in one iterate, right? That's basically what all of these inequalities were doing, is basically just that plus a little bit of Cauchy-Schwarz inequality. And then finally, we used a very typical strategy in the optimization world, which is that oftentimes it's easier to bound our sort of amortized error relative to the current one. That like it turns out like looking at the objective value averaged over the last several iterates is sort of a stabler number to analyze than the objective in any single one. And indeed, in this particular case, that's what led us to our final inequality by kind of averaging and noticing that our algorithm was monotonic. This is a tough proof. This is tougher than most of the stuff we've done in this class. Obviously, I'm not going to ask you to regurgitate it in an exam, but I do think it's important to kind of see, like, this is the simplest case of gradient descent converging. And already, it's pretty hard to justify. like it required a lot of work and very careful analytical style argument. And indeed, if we kind of relax any of the assumptions of this theorem, it no longer works. Like this is one that just barely holds together, right? And so I think that we can kind of take for granted that gradient descent converges in a more generic case is sort of miraculous when you're using a constant step size. And this begins to justify why people do all kinds of crazy engineering, whether it's line search or coming up with interesting, weird learning rate schedules or what have you. These are basically ways to get around the fact that the conditions for gradient descent to actually reach a minimizer are a little bit tricky and hard to arrive by. Yeah? In any event, this proof is perfectly valid, and actually for many problems you encounter in like operations research, like the world where problems are convex and well-behaved, this theory is actually enough. I think one reasonable question you might ask is how might you actually get a Lipschitz constant in practice? And I think the answer to that is it's really, really hard. So I think a typical thing to do is to look at your problem and say, oh, like at the very least, it kind of looks like least squares or whatever. So like I think that there is a Lipschitz constant. And I try gradient descent, and if it doesn't converge, I say, well, I guess that wasn't the Lipschitz constant. And then I try again with a smaller step size, or I use one of these learning rate schedules. Incidentally, this proof can be repaired for the case where L, or rather where T is a function of K. It's just this summation argument becomes a little uglier. That's all. I saw a hand over here somewhere. Yes?
Could you remind me of when we showed that like the sequence of errors is monotonic?
Oh, yeah. In fact, is it sitting on the board? It might be. Oh, yeah. In fact, condition 1, that's right. So notice, so remember y was f after one step of gradient descent. And notice it is strictly, in particular, this is a positive number. So it's never the case that the f of y is larger than f of x. Yeah. Thank you for I waved my arms around because I couldn't see it, and I was trying to sneak it past you. But that's really what's justifying this averaging argument here. Yes, Hamid. Did we use the triangle inequality? Ah, you're right. I guess just Cauchy-Schwarz. I would argue they're kind of the same. But you're right. You got me this time. Any other questions? Fabulous. So now, at the very least, we can see that the gradient descent like still converges, even in this other extreme case where rather than when doing line search, we just use a constant. But notice that these conditions are way tougher to check than the Wolf conditions. Right? Wolf condition you can just check during your algorithm, right? Because it's just a condition on each tk. This one like requires having global knowledge about the shape of your function, like a Lipschitz constant here, and like you need to kind of sit underneath that in your learning rate to make sure that you converge. Yeah, so these are the sort of two extremes of the story. Okay, I should briefly mention, I decided to jettison from this course largely because I haven't written it up, and because this course already packs in way too much content. There is another class of algorithms out there called accelerated gradient descent. The one that's sort of theoretically justified that people know is something called Nesterov descent. The one that people actually use is an algorithm called Atom, and then every year the machine learning community proposes some small variation thereof. These are basically some version of gradient descent where you keep some knowledge of the past gradients around. And typically the picture that people draw is that they kind of build up momentum. So like for instance, let's say that I did gradient descent with a constant step size, and the step size was just too small, right? So now what's going to happen? I step downhill a little bit, I recompute my gradient. I step downhill a little bit, I recompute my gradient. And every one of those steps, the gradient doesn't change that much. Do you see that? Because like if I take an itty bitty step, chances are the direction of steepest descent didn't like wildly change and like move to the left, right? On the other hand, if I took too big of a step, then I'm in like some completely different part of my function, and now for all I know, the gradient is like pointing behind me, right? And so what these algorithms attempt to do, and the kind of beautiful thing is that you can do it in a nice, like a theoretically justified fashion, is they keep some momentum around. So in other words, like let's say that I took my gradient and I kind of averaged it with the gradient I had in the last step, or maybe even extracted a little bit, like just added it instead of averaging. Then do you see what's going to happen? Like if I keep walking downhill in the same direction, then maybe I build up confidence and I just walk faster and faster in that direction, like skiing or something. On the other hand, if my gradients keep flipping around direction, if I average with past iterates, then the norm will kind of go to 0, right? And so these things are sort of adaptively scaling the directions in which you move. The really beautiful thing that Nesterov, to my knowledge, basically pulled up out of a hat, because these Russian guys are impressive that way, is that if you do that in just the right fashion, you can actually get a better convergence rate. So in particular, our gradient descent is linear. Do you see that there's a 1 over k there? But you can do slightly better than linear by using these kinds of accelerated techniques. And moreover, they seem to make a big difference in practice in certain corners of machine learning. Actually justifying these techniques is really tricky. Like the actual proof is pretty yucky. And I've never found a good pictorial argument. Apparently, this is actually a famously hard thing to do. But algebraically, it's pretty straightforward. The atom algorithm, I think, is actually kind of the cleanest one to derive heuristically, and kind of what it's doing is correcting for the kind of variance or covariance that you see of the gradients over time. Yeah?
I was wondering, when you say it's better than linear, is it still sub-quadratic?
Yeah, I don't think it's all the way quadratic. It's like somewhere in between. I could be wrong. I forget offhand. But in any event, I just thought I would mention these because they are important algorithms in the kind of numerical universe today. And I think if you take an advanced machine learning course that focuses specifically on this kind of problem, you'll see that that's sort of the next thing to work on. Those proofs are kind of yucky, though. Yeah. Good news is they're implemented by software. OK. Actually, the algorithms themselves are pretty simple. It's just the proof is ugly. All right. So far, we've talked about gradient descent, which is like the world's goofiest, dumbest optimization algorithm in some sense. If we go back to our root finding lecture, like actually we just asked, like, can we get quadratic convergence? The answer is absolutely yes. Because remember, for differentiable functions, finding an optimum is kind of like finding a root of the gradient, right? In other words, finding a minimum is kind of like setting grad f equal to 0 and doing root finding on that, right? It's not exactly the same because local maxima also have that property, so you have to be a little bit careful to not be in that regime. But for example, for convex functions, like we need it for gradient descent anyway, that can't happen. And so you could very reasonably use Newton's method to solve these problems. Now, version 0, I think the way that you could derive Newton's method for optimization is kind of twofold. One is to directly lift from our root finding lecture, right? We already know how to do Newton's method for root finding. Remember, it's like df inverse times the value of f. But f is the thing whose roots you're trying to find. So if we substitute in the gradient, then we end up with a Hessian. I think there's a cleaner derivation of Newton's method for optimization, which is very simple on the board here. Let's say that I'm at an xk in my current optimization technique. I can take a second order Taylor series, right? So now it's f plus the gradient of f plus the Hessian. Hopefully this Taylor series makes sense. And remember what Newton's method does for root finding. It like linearizes, finds a root, and then uses that root as my next iterate. Does it make sense to linearize and optimize? If you think about it, it kind of doesn't, right? Linear functions don't tend to have minima unless you have a constraint, right? They just keep going smaller and smaller and smaller. And so instead, maybe you take two Taylor series terms, and now you can optimize this thing, and it's a quadratic. Yeah. So by now, you guys, since you just took your midterm, can do this all in your sleep, and you'll get some iterate that looks like this. Yeah. And this is called Newton's method, and it inherits all of the properties that Newton's method had before, namely that it converges quadratically so long as xk plus 1, or rather, so long as the xk's are sufficiently close to a local minimizer. Yeah? Any questions so far? I think this part is much easier relative to the hot mess that we just did on the board. OK. So this is Newton's method, and actually for like small to medium scale optimization, lots of people use it. There are many challenges with Newton's method that come up. Now, specifically, I think one good place where Newton's method tends to fail, if you use the algorithm as written here, is in physical simulation. So for example, if you're simulating like elastic bodies or fluids or whatever, there's like little optimization problems come up as subsets of those algorithms. But they tend to be very unstable, and they tend to have the property that the Taylor series for f changes very quickly as you move x's away from these points. So in other words, this kind of quadratic approximation goes kind of stale. And so a very typical thing to do here is basically to just introduce line search. In particular, it's perfectly fine to call this h to the minus 1 grad f a search direction for gradient descent, or for not gradient descent anymore, just optimization, right? Like dk in our Wolf condition. And now to search along that thing to find something that satisfies Wolf conditions. Very, very typical procedure. So if you use software like SciPy and it asks you for a Hessian, that's what's going on behind the scenes. Does that make sense? Now, here you have to be the tiniest bit careful. So this is going to take care of the case where like your Hessian goes stale. So for example, if you have a function, it's like going down and then up and then down, like this kind of thing, which is very clearly not quadratic. Then like if I go too far away, my quadratic approximation is no good. Are there other problems here? So for example, let's say that I initialize Newton's method for optimization at a point like this guy, right? So what does Newton's method do? It finds a second-order Taylor series approximation about that point, and it optimizes it. Probably, I would guess, the second-order Taylor series is going to look something like that. Is that a very good-looking problem if our goal is to minimize? No, this is a hump instead of a bowl. That's not what we want. And in fact, in this case, Newton's method gets me closer to a local maximum. That's exactly what we were trying to move away from, right? So how can you detect that? Some review from a couple lectures ago. So if I look at h, what went wrong in this particular case? In other words, like if you look at the second derivative of this function, yeah, it's negative. It's a parabola that points down. That's not so good, right? More generically, if I look at h, now h is a symmetric matrix. What do we know about symmetric matrices? Fun midterm review. Yeah, that's right. It has a full set of eigenvalues. And if any one of those eigenvalues is negative, then in that direction, f curves in the wrong direction. Sorry, hopefully that sentence parsed despite some poor choice of words. Yeah? And so the reality is that actually you have to be very careful, even if you do line search, right? Like if Newton says to move this way in this function, no matter how small gamma is, my function didn't go down, it went up, right? So in fact, this is not generically a descent direction. And so you can end up in cases where the Wolff conditions are impossible to satisfy. And so very typically what you have to do is to take h, look at its eigenvalues, and mess with them to make sure that you don't end up in that regime. So there's some very fun tricks you could do. One thing you could do is like try to compute the Cholesky factorization of h, right? If it fails, then you know that it's not positive definite. So then maybe you just like resort to gradient descent, do a few steps of that, and then try again. Perfectly reasonable. But actually, it turns out what's standard in physical simulation are to use a lot of other really cool tricks. So for example, one optimization kind of strategy you could use is as follows. You could solve the following. You could look at what is the best approximation of hk. Actually, you can use Frobenius norm or 2 norm. I believe you'll get the same formula regardless. Subject to the constraint that h is positive semi-definite. So in other words, you've got this like bowl-shaped function in some directions, and then some directions it points downward, and that's no good. So I kind of want to throw those directions out and then like replace my Hessian with something that's bowl-shaped. Does anybody know what the outcome of this is? You're really good at SVD in your head. Okay, so we're going to just have a spoiler alert on this one. And so in particular, let's say that I compute the eigendecomposition of this guy, right? So this is going to look like eigenvectors times diagonal of eigenvalues times eigenvectors transpose, right? I think I got that right. Yeah. And then it turns out that h is actually very simple. It's simple to write down mathematically. It's not so simple to compute, which is the following. You just take all the negative eigenvalues and you clip them like that. That turns out to be the closest projection of hk onto positive definite matrices. And so a very standard thing to do, I think you see this a lot in the computer graphics community and physical simulation, is to take your Hessian for your full problem, compute its spectrum, zero out its negative eigenvalues, and then just assemble the whole thing back together and use that for your Newton step. There's a few issues with this algorithm. One, by the way, what is this function? Does anybody recognize this from neural networks? This is ReLU. That's right. So in some sense, you're computing ReLU of your Hessian matrix, which is absolutely right. ReLU has a really annoying property, which is that it's very hard to approximate with rational functions. And so because of that, it turns out computing this h is actually very expensive. You have to compute the full spectrum, clip, and assemble the thing back together. It's not like a good approximation, like just directly in terms of hk, like something involving its inverse or something like that. I know because I wasted half of my postdoc on this about 10 years ago. Moreover, so this thing is relatively expensive to compute. Is h typically invertible? Pretty clearly not. Do you see that? So like h, if this formula did anything interesting, h is no longer invertible because I replaced one of its eigenvalues with 0. So then you start having to hack yourself even farther, like adding a small multiple of the identity to h or something like that. So in any event, that's one of the sort of standard tricks people do. And in certain cases, you can show that this leads to quadratic convergence if you're very lucky. You'll notice the theorems are going to start getting fuzzier because that's actually really the case in this corner of math. A different policy that I think we can all agree is like a pretty reasonable one is just don't do Newton for a while. Just take gradient descent and then try again later. Yes. H and Z. Oh, this thing? I can never draw this well. This means semi-definite, positive semi-definite. So it's like you took an inequality sign and you kind of like gave it a little zhuzh. That means positive semi-definite, or all positive eigenvalues. Yeah. It's greater than or equal to 0, which is kind of like positive, but I mean it on the eigenvalues, right? Which is equivalent to positive semi-definite. And it's just like the inequality sign with like a little curve to it. Yeah. Good question. A third thing people do sometimes is they add a multiple of the identity to H that turns out to be kind of like averaging between gradient descent and Newton's method, if you work it out. And there's actually one fourth thing that I thought I'd mention very briefly, because it happens both in physical simulation and in machine learning, which is as follows. Very typically, we have the following situation where the optimization problem that we're trying to solve is really a sum of a bunch of little terms like this, right? This happens, for example, you have a loss function applied to a bunch of data points, or in physics, if you're like doing simulation on a triangle mesh, then maybe there's like one term for every vertex or something like that. So it turns out the standard of the physical simulation community, which I've also seen a little bit in learning, is really sneaky. It says the following. So for one thing, by linearity, the Hessian of f is equal to the Hessian of each fi, right? So that's pretty clear, just by linearity of derivatives. Now, oh no, I erased it. Like, remember one thing we could do is compute the negative eigenvalues of h, clip them at 0, and then put the whole thing back together. Here's the sneaky thing that the physical simulation community does. They say the following. Let's say that we call this the projection of HF, where here I mean the projection onto the semi-definite cone, if you want to be fancy. They use the following approximation, which is that it's the sum over I of the projection of HFI. Now it turns out you can't do this. Like you can't like take a big sum of things, clip them all to be at, this would be like kind of like saying like taking a bunch of numbers that you want to clip at 0, but those numbers are summed together, and instead clipping together all the things that are summed at 0 and then summing them. Obviously those are not the same. But it turns out there's a really clever reason why people do this. In a lot of problems, like for example, problems that happen on graphs and networks, each of these individual FIs only involves a few elements of X. Right? So think about a problem like I'm modeling a social network, it's on a graph, and I have a bunch of terms that involve like the coupling between pairs of vertices or something like that. Right? So like Fi only involves like these two guys, which is like x1 and x2. Right? Then the kind of cool thing that happens is the Hessian really is a matrix that just involves these two elements of the vector. So in other words, your H kind of has a bunch of zeros, and then just like some little tiny block, and then a bunch more zeros, right? So for example, in physical simulation, you have like some triangle mesh that's sitting underneath your physics. Then very typically, your Hessian involves like a vertex, and it's like 6 neighbors. Well, in that case, this projection is on like a 6 by 6 matrix instead of an n by n matrix. And then you assemble them all together, right? And so this is the standard in a lot of physical simulation. The other kind of happy byproduct is this thing tends to be invertible when this one is not, because you've kind of overestimated a lot of your Hessians. Although, of course, it's invertible for a reason that like isn't so great. Oh. So anyway, I thought I would just briefly mention this other trick, which is to say if your optimization objective is really the sum of a bunch of other things, you could project the Hessian of all those other things and add them together. That is not the same as projecting the sums guy. However, oftentimes, if your FIs really only involve a few elements of your vector, then this projection is a lot cheaper. This even happens in machine learning. So for example, certain data points really might only affect a few neurons in your neural network. Then really the Hessian only involves that subset of variables in your problem. Yeah. So anyway, that's just a fun side note. So at this point, we're basically an entire lecture behind our course schedule, but that's OK. I will foreshadow our next problem, and then rather than diving into a big, ugly calculation right now with 5 minutes left, I will let you think about it, and we'll race through it next time. So remember in our root finding lectures, we talked about all these different techniques for finding zeros. We started out with like bisection, and then we did fancy things like secant method. And we asked this question, can we make secant method work for higher dimensional functions? And that led us to an algorithm called Broyden's algorithm. Remember, and so what did Broyden's method do? It basically avoided computing derivatives in the root finding procedure for functions on Rn, right? Now, you could ask exactly the same question here, like, can I avoid computing derivatives in the course of doing optimization in a way that still preserves some of the nice convergence properties of Newton's method? And the answer is yes, obviously, or I wouldn't be telling you about it. And in fact, you could just apply Broyden's method directly. You see that? Because Newton's method is just root finding on grad f. So you could do that, and that would avoid evaluating your Hessian. But one thing that we actually suggested a few lectures ago is that we might be able to do better. So in particular, we're going to be in the following situation, which is we're going to try and optimize functions whose gradient is easy enough to compute. That turns out to be a very typical assumption in 2025. Software like PyTorch is very good at this. But whose Hessian might either be dense or hard to compute. Right? So for example, if I've got like 1,000 variables, it might be OK to compute a vector of 1,000 elements, which is the gradient. Right? In some sense, you can avoid 1,000 variables since your iterates are in R1000 anyway. But you don't want to compute a giant 1,000 by 1,000 matrix, and moreover, you certainly don't want to invert it, right? And so that is sort of like the motivation we had behind Broyden's method. Yeah. Now, if we go back to the Newton's method, a formula we had before, like here, we could apply Broyden's method to basically approximate HF, and that's perfectly fine. You can do that, and it'll converge. But the h's that you'll get are kind of weird because Broyden's method doesn't know one additional fact about optimization, which is that h is a symmetric matrix. Right? This comes from derivatives commuting. And so instead, there's an entirely new class of algorithms, which is what we'll cover, I guess, next time, called quasi-Newton, because they're like Newton, where essentially you're trying to approximate the Hessian in this case, using the strategies that are similar to Broyden's method, but that preserve a little bit more properties of Newton's method than the Broyden approximation, right? So we're going to be in this regime where the gradient of f is known, or like you can get it from backprop. You don't need like a formula for it. And the Hessian is either unknown or hard to compute. And essentially, we're going to consider algorithms that take place in the following form. Notice that if bk happened to be the Hessian of f at xk, we would have Newton's method. If bk happened to be the identity, we would have gradient descent. And now we're going to wedge a lot of algorithms in between those two. And these are these quasi-Newton methods. And what they're going to do is try to apply approximations like Broyden, but we're going to force b to be symmetric. Okay? And so our next lecture, what we're going to have to do is like kind of a souped up version of Broyden's method. Remember what Broyden's method did? It like applied a secant style update to our derivative and sort of said like, what is the matrix that changes the least in a least square sense, but enforces this one-dimensional change? But now, sadly for us, we need to preserve symmetry when we do that, so we're going to have an additional condition to that. I see you, but I'm going to take one more minute. Moreover, so if you remember our Broyden update, it looks something like this, like min over Jacobians of like dk minus 1 minus d squared, subject to d times like y minus x equals, or f of y minus f of x in the Broyden thing. God, this eraser is terrible. Right, it was something like that. Now, another thing that we're going to re-examine in our next lecture is this norm here. Now, in particular, let's think about your Hessian matrix for a second. Let's say that I have some mathematical model that's trying to predict the height of a plant from, I don't know, the amount of water that I pour on it and the distance that my car travels to Home Depot, right? This would be a weird thing. Then what are the units of the Hessian matrix? Well, there's water, which would be in like gallons, right? There's distance to Home Depot, which is in light years. Okay, so then like the upper left would be like, height per gallon squared. The upper right would be height per gallon light year, and so on. Does it make sense to compute this Frobenius norm? Not really, right? We're like adding together a bunch of numbers that don't have the same units. So this like lazy update from Broyden method kind of doesn't make sense for optimization. So what we're going to do in our next lecture is a few things. We're going to switch our norm around to one where the units make sense. And we're going to enforce symmetry, and then we're going to prove a big, giant, happy formula, which is what people use for quasi-Newton methods. And in particular, we're going to derive two algorithms in one called BFGS and one called Davidon-Fletcher-Powell, which are basically variations of the same thing. Hamid, you had a question like 10 minutes ago before I started talking. That's a good question. No, we are not going to preserve positive definiteness. So then you still need these projections we talked about before. Yeah. You could ask a different question, which is, can you incorporate that into these updates? And I think the answer is, kind of. Yeah. All right, folks. With that, don't forget your homework. It's due on Wednesday. We will grade your exams soon, I hope. And have a delightful rest of your Monday. Man, do I need to go to the bathroom. Oh, God, I'm dying. Oh, and I didn't actually record the lecture. Great. All right, well, I will get it from our colleagues in the office.